All right, so in this video, I'm going to talk a little bit about angular momentum and rotational kinetic energy. And so let me say that the explanations that I'm going to give here are very short, very direct to the point, very surface level. And so for a deeper, more in-depth explanation, I definitely recommend the AP Live YouTube videos. I can't really do it any better than they can. They'll go into a lot more depth than I will. But these are just meant to kind of get your feet wet and just to give you a super short introduction to these two topics. And so if we remember from our translational stuff, which is another word for linear, our linear momentum is given by P is equal to mass times velocity. The units here are units for mass, kilograms, units for velocity, meters per second. So therefore the unit is kilograms times meters per second. And that's what we call linear momentum. And in terms of its rotational counterpart, we represent that with an L. And just like we did with other quantities in rotation, we replaced our mass now with the moment of inertia, because the moment of inertia tells us how the mass is distributed. So we replace that with our moment of inertia I, and then we replace the tangential velocity with our angular velocity. So therefore, our formula for angular momentum is given by L is equal to I times omega. Angular momentum is equal to moment of inertia times the angular velocity. Where are the units here? The units are a little different. The units are going to be kilograms times meters squared per second. So it's kilograms times meters squared per second for our unit. It's kind of different. So actually, let me write that above these two. So this one's kilograms times meters per second. This one is kilograms times meters squared per second. It's a little different. All right, and then kinetic energy. Kinetic energy, our translational formula is 1/2 mv squared. This tells us about the energy of motion that an object has. Well, we do the same process of converting mass to moment of inertia and velocity to angular velocity. And so we're left with 1/2 I times omega squared. And the units for this are just joules. So I'll write above it joules, because it's still a unit of energy. And so it's measured in joules, J for joules. All right, something important to note. First off, although energy is conserved, kinetic energy is not usually conserved. You usually lose a little bit of kinetic energy in the form of heat or sound or things like that. So kinetic energy isn't usually conserved. But just like regular momentum is conserved, angular momentum is conserved. And the way we write that then is we write L naught to represent the initial angular momentum is equal to L final to represent the final momentum. The only time that this is not true is when you introduce some external force, so something outside of your system. But when you take, if you take your system as including that outside force, you realize that angular momentum is still conserved. So this statement that angular momentum is conserved is always true. Now, how you define your system will tell you if there's some external force affecting that isolated system, but angular momentum is always conserved. How does this help us? How does that help us solve problems? So I'll do a couple of videos on solving problems involving angular momentum and kinetic energy, but for now, think about it like this. So if our formula is I for the moment of inertia times omega, and this quantity is conserved, meaning it's the same before and after, meaning whatever value you get for the initial angular momentum should be the value that you get for the final angular momentum. What happens then if we decrease one of these values? So for instance, if you've ever seen a figure skater, when figure skaters are rotating and they pull their arms in like this, their rotation, their angular velocity is going to increase. They'll start spinning faster. Just like if they extend their arms like that, their angular velocity will go down. It'll go down because of conservation of angular momentum. What that says is that as the moment of inertia goes up, the angular velocity must go down. Why is the moment of inertia changing if a figure skater brings her arms in? Well, keep in mind the formula for a moment of inertia. It tells us about how the mass is distributed. And if the mass is distributed closer to the center, that means it has a lower moment of inertia. As that mass goes closer out, or farther out, I should say, that moment of inertia increases. And so you get this relationship where Increasing the moment of inertia decreases the angular velocity, and increasing the angular velocity decreases the moment of inertia. So if the moment of inertia goes down, figure skater pulling her arms in, or his or her arms in, the angular velocity must go up because of this relationship here. So that's conservation of angular momentum. It's really useful when you're solving problems for the same reason that conservation of regular momentum is useful. It allows us to analyze collisions and objects coming together and sticking and things like that. So I'll make a couple videos on solving problems involving angular momentum. All right, that's it.